This is question 16 from the first CSAT sample paper. So this question is a little bit hard to interpret, but this is the way I interpret it, and I think this is the way that gives a sensible answer. So we're looking at the number of years for an interest rate of R% to double your investment. So suppose you invest £100. Each year you multiply that amount by 100 plus R hundredths. So 100 plus R% of that is what you have after 1 year, and then after 2 years you have 100 plus R% of what you had after the first year, and so on and so forth. And eventually you'll have twice as much as you started with, and the number of years after which that happens is n. And we're told x over r approximates n, where x is the number we have to find and r is the interest rate in percent. You'll have to figure out exactly what this means. We're told this works when r is small, and we're also given a hint that we should use part of a previous question, and that previous question gave us the Taylor expansion for log, or a Taylor expansion for log. So it looks like we're going to have to use that in some capacity. In any case, if you want to have a go at this question yourself, pause the video now. Okay, so first of all we want to write down another equation relating n to r so we can try to see what this gives for x. And in particular we want to interpret what n means. It's a number of years for R% to double your investment. How can we express that? Well, we're basically saying r is a percentage, so if we do r over 100, that's the fraction of your investment you gain each year. Well, in other words, if we do r over 100 plus 1, that's what you multiply your investment by each year. And we're saying if you do that n times, so to the power n, then you'll have doubled your investment. So I've written this 1 plus r to the 100, so this is what you multiply your investment by each year, to the n, because we're doing it for n years, is equal to 2. Because we want to double our investment, so we want to have eventually multiplied our initial investment by 2. So we want this factor we're multiplying by to be equal to 2. And now it's clear where logs come in, because we want to get n in terms of r, and that means we want to take logs to get rid of the power. So if we take logs of both sides, I'll do it with the natural log because that's what we have the Taylor expansion for. So n log 1 plus r over 100 equals log 2. Just taking logs of this side and bringing down the power in front. And now we were given that Taylor expansion for 1 plus x, log of 1 plus x. And that's good because this is of that form. So it makes sense we'll try and expand this and see what happens. Bear in mind we're talking about an approximation when r is small, so it makes sense what we'll do is look at the Taylor expansion and see what happens when r is small. So log of 1 plus x, I just wrote out the definition we're given, is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, etc. And they didn't say this in the previous question, but I've said this happens if x is less than 1. So I put an asterisk by this because it's not given to us, and also this isn't a necessary condition. We can also have x equals 1 and it will still work. But in particular this works whenever mod x is less than 1, so whenever x is between minus 1 and 1. And that's fine because r over 100, we're told r is small, so definitely it's not going to be 100%. We're not getting our full investment every year. So r over 100 is going to be less than 1, and that's fine. So this will work. And you can imagine if it was likely this wouldn't work, then they would have given you this constraint in the question. But it's still useful to know. Okay, so let's plug in r over 100. So log of 1 plus r over 100 is x is r over 100, and then we got minus a half of r over 100 squared, and then I'll just put plus dot 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 because I'm not going to care about the rest. So in fact, when r is small, the only term that's going to matter is this first one, because r over 100 is going to be even smaller, and when we square it, cube it, etc., it's going to get too small to matter. And this is a useful principle in general, that if you have a Taylor expansion and the x is very small, and you don't care about the higher powers. So basically saying this is going to approximate this as, well, when r is small. I'm going to talk about that in terms of limits. So basically this tends to this first term as r tends to 0. So saying this tends to r over 100 for r small, so as r goes to 0. So now we want to talk about n. N was log 2 over this, from this line. N is log 2 over log of this, and therefore that's 10 to log of 2 over r of 100, and then we can just rearrange that, multiply by 100 to get 100 log 2 over r. So basically n is approximating 100 log 2 over r, and we also know that x over r is approximating this. So let's write that. X over r is approximating this, or I'll do it with the limit symbol again. X over r is approaching 100 log 2 over r, as r goes to 0. And if that happens, what does x have to be? Well, since r features in exactly the same function, it's just dividing by r on both sides. If these two things are approximating each other, as r goes to 0, then x should be, well, it could in fact only be very close to this, but it has to be arbitrarily close to this, so we can just take x to be equal to 100 log 2. And that's clearly what the question intends. It intends just one value. So we choose x equals 100 log 2 to make this an actual equality. Okay, so that's our final answer.